following along in your notes, you may notice that we've skipped a few pages. That was intentional, no need to be worried about that. We'll eventually get to all this information. So for now, we're going to focus on this concept called sampling distribution of the mean. And this is a very important concept because it's going to connect a lot of ideas we learned about probability to our goal of statistical inference. That is, how do we go from using a sample, a subset of the population, to make predictions and estimates about the entire population? This idea is key to being able to make that inference. So let's start with a concrete example first. Suppose we're interested in average box office earnings of the top 50 grossing films in the US. To do this, we're going to take a random sample of 5 movies. So there's this idea of inference already. Our population is top 50 movies, made the most money. Instead of looking at all 50, we're going to take a random sample of 5, and we find the sample average to be $325 million. And then, unknown to you, the actual population mean. So this sample average, remember our notation here, that's X bar. And they're telling us the population mean, mu, is 383.1 million. We also know some other information about the population because this is a contrived example. I was actually able to obtain the population, all 50 top money-making films. Here's a histogram of the population. The median earnings, these are in millions of dollars. Here's the standard deviation, and then just a little bit of review. The shape of this distribution would probably be best described how? Correct, right skewed. Okay, so this is our population of interest. We know with this whole population, we know all kinds of information about this population of 50 movies. Let's go through and add some terminology to familiar terminology. We're going to review the idea of population distribution. Remember, this is our entire group of interest. It's described by parameters. Instead of looking at everybody, we look at a sample. That sample can be described as data, and we can look at the distribution of the data. And any summaries are called statistics, such as the sample mean. Then we're going to add this new bit of terminology called sampling distribution. Before we do, let's kind of draw a picture to illustrate what's represented in these paragraphs. So for our picture, I'm going to start off with something we saw at the beginning of the course. This oval kind of shape is going to represent our population. I'm going to call this our population distribution. Or in other words, this is information on what the population looks like. So in our particular example, this describes the earnings of all 50 movies. That's our population. These top 50 money-making films. Population distribution describes those earnings for all of them. And we describe those with parameters like the mean, which they tell us is $383.1 million. Population standard deviation, $141.8 million. And we know the shape is right skewed in the median and so on. Our goal in statistics, what we do in practice, is to collect a sample or a subset of the population, and that sample can be described by the data distribution. So this, let's say, describes the earnings of, instead of all 50 movies, our sample of 5 movies. And they tell us that, and for example, if I collect a sample of 5 movies and I calculate the mean for that sample of 5 movies, they tell us that one possible value might be $325 million. This makes sense. The whole population is 383.1. If I only look at 5, not all 50, I'm not going to get the same average. I expect this to have some variability between my data, a subset, and the whole population. Now we're going to add on to this idea. So far this should be familiar. However, what if I took a different subset? I'll call this sample 2. And that was a sample of a different 5 movies, not the 5 I took up here. And I calculate the average for those 5 movies. What would we expect for the average of these 5 movies? Is it going to be $325 million? No, probably not, because it's a different 5 movies. Is it going to be $383.1 million? No, probably not, because it's a different 5 movies. So it's its own 5 movies. I'm going to get a different value. I don't know, maybe 387 million. If I took yet another sample, I'll call this sample 3, of a different 5 movies yet again, I'm going to get yet again a different sample mean. I'm just making these up, by the way. But we have this idea that because I'm looking at different samples, I'm getting different sample means, and so on. There's actually about 3 million different samples I could possibly take of size 5 here. So I'll call this sample something, a large sample. I've done this a bunch of times, 3 million plus times. I'm going to get yet a different mean for this one. So we have this idea, remember our big picture. In practice, we're not going to take a bunch of different samples. We're going to take one sample. We're going to use that one sample to make predictions about the whole picture, the big population. However, we need to think carefully about this notion that this one sample is what we say it is, just one sample. If I took a different sample, I'm going to get different estimates. And that's important because we're using these estimates to make predictions about the bigger population. So we need to understand how these different samples relate to one another and how they relate to this goal or this target of our population distribution. So here, that's supposed to be a curly brace. This is our sampling distribution. And the sampling distribution tells us what all these different statistics are going to look like from different samples. So here, I'll just say that as each of the samples will give different sample statistics. And in this case, our different sample statistics are the mean. So these different X bars. They could be different proportions, and we'll see that later on. And the sampling distribution is going to tell us what all these different X bars look like. So I'll say the sampling distribution tells us what the possible X bars look like. Again, this is really important because in real life, we're not going to take a bunch of them. There's a theorem we'll see shortly that will tell us what they look like if we were to collect a bunch of different samples and calculate the statistic for each sample. But that's important information to know again because we're going to, in practice, collect one sample use it to make predictions about the whole population, but part of those calculations need to include this idea that that's not the only sample I could collect. So let's take a look at what we're going to see here if I collect different samples. So here's our actual population, the top 50 money-making films, and this might need updated just a little bit. For example, I think Black Panther made a lot of money, but it's not included on here. If you're a movie buff, you might enjoy pausing and perusing this. But anyway, let's think through this setting. Suppose I use our calculator, if you remember using randint to generate a random sample, or using the random digit table to select a random sample. So we're going to randomly select two numbers representing two movies, and just for simplicity, I'm going to use the table. So maybe let me start here on this first entry. So 27 is my first two-digit number, so that's going to be the first movie in my sample. And then 66 is my next two-digit number, but my population only goes to 50, so I'm not going to include that. 07 is my next two-digit number. I've got a movie with those digits, so we'll go there. So then we'll look down here at my two randomly selected movies, 27, so Furious 7, and the earnings for that were $351 million. Then my second movie was 7, Star Wars, Phantom Menace. Might be watching that for movie night soon, $474.5 million. So those are the earnings. And then, so my sample of 2, there's the actual observations. And then I could find the mean of my sample of 2, 351 plus 474.5 divided by 2. And I would get my x-bar, or mean, for this sample of 2. So probably just over 400, somewhere around there. So imagine if you did this, you might get a different two movies, maybe Minions and Spider-Man. I have small kids, so Minions has definitely been on our movie night. So maybe you get these two movies and find the average of these two, which would be about 336.25, which is different from my two movies. And we did this. Everybody in the class randomly selected their two movies and got the average earnings of their two movies. What I would typically do next in a face-to-face class, after everybody's obtained their samples of two movies, you might come up to the board and draw an x-bar where your two movies, the average of your two movies. So for example, the first one I did a moment ago was the average, the sample mean was somewhere around here in this region. That second example I did, it was more like right here, the 336. Maybe you took a different sample of two movies, got something down here, and so on. So if we did this activity where everybody took their own samples of two movies, and I'm kind of glancing at some old data that a previous face-to-face class has used, you would start getting something that looks like this. Okay, so everybody in the class would have their own x-bar represented on here for the average of their two movies, and we would get something like this for our averages for samples of size 2. So these are x-bars, or sample means, when everybody took a sample of size 2. Now, rather than having everybody repeat this again, I went ahead and wrote a program to simulate doing this for samples of size 10. So n equals 10, we get these means, and then 20, we get these means. So let's kind of zoom out a little bit and look at the general trend, what's going on here. So let's make some observations. Notice we're doing the same process, taking a random sample and finding the mean of our sample, and doing that lots of times for different samples to see how it behaves. The only thing we're changing is we're looking at this when we take samples of 2, samples of 10, and samples of 20. So first observation, let's talk about any trends in the center of these distributions. Now notice I try to be really careful to line these up on the same scale, 0 to 800 million. And on this same scale, if you kind of had to eyeball the center on these, hopefully you're seeing this common trend that, wait a second, they're all lining up at this pretty much exact same place, regardless of the sample size. And this, in fact, should always happen. This is cool fact number 1 regarding center. Regardless of sample size, the sample means are centered at the same place. And notice what this same place is. It's a little less than 400,000, and that number should sound really familiar. In fact, that is our mean of $383.1 million is represented by this line. So that'll be our first observation here. Regardless of n, okay, so by that I mean in all 3 of these cases here, the sample means are centered at and just a reminder of our notation, sample means, that's x bar. So the sample means are centered at the population mean. And remember that notation is mu. So this is should be really comforting, the fact that we're using the mean of data to estimate the mean of the population. And the mean of the data, even from different samples as it varies, it's going to vary centrally around the population mean. Now the next thing, let's observe the shape. Now if you remember, the original population was quite right skewed. In this case, for samples of 2, we notice it's still, the sample means are pretty right skewed. Still some right skewness for 10. When we're looking at 20, now this looks kind of symmetric, looks pretty bell curve to me. So that's our second cool fact, is that when you have a small sample size, the sample means will have a shape similar to the original population. But as your sample size increases, that shape converges to this normal distribution, which is why z-scores and the normal distribution are so important. So I could have an original population that's right skewed, left skewed, any kind of wonky, crazy shape. And if I take a large enough sample size, the shape is going to come to be this nice, tidy, neat, symmetric, normal distribution. So let's add that down in our notes. We'll say when n is small, the x bars have a shape similar to the population, the original population. And then as x increases, or n increases, their sample size, it becomes normal. So as n increases, the shape becomes normal. Okay, really cool, because that means the z-scores and the normal CDF, all that we worked on so hard previously, is going to be useful in basically the rest of the semester. So that stuff's not going away. All right, last observation to make is about the spread. So notice for a small sample size, the spread is pretty large of what I can get from sample to sample. But as my sample size increases, the variability in my possible statistics is decreasing. It becomes much less. I'm not going to be as far away from that target parameter, the population mean. So we'll say as n increases, the spread decreases. And let's kind of give some vocabulary to this. The spread or the variability of a statistic is called the standard error. Let's say the variability of a statistic is called the standard error. And we're usually going to abbreviate that with just a capital SE. And if you remember way back when we talked about that study about beauty sleep, you'll remember they had SE in the results section, and that's what they're talking about, the standard error. How much do we expect this calculation to vary from sample to sample? And in this particular case, our standard error for the mean, so I'm going to use this little subscript x bar because I could calculate the spread or variability of a different statistic as well, is sigma, the original standard deviation for the population, over square root of n. So this mathematics makes sense with what we saw in our pictures. N is the sample size increases. This whole fraction is going to decrease, which is what we saw. As n increased, the variability or the spread decreased. We'll do one more video where we firm up this idea and check it out in an example.